this is Arnoud, WizBiz.com, and in this video I'm going to explore a very simple way for you to switch a load like a lamp, an electromagnet or a motor directly from your Arduino or Raspberry microcontroller output. And we're gonna investigate how to limit the current of such a driver and even if we can equip it with a protection against short circuit. These are rather universal principles that are certainly useful for your own electronic projects. So let me give you a little bit of background with these modules. Anyone who has followed my tinkerings here on YouTube must have noticed that I enjoy making DIY modules that are fully compatible with these classic fischertechnik electronic modules. And I like to do that in form and with these 3D printed cases, but also from the point of signal levels that were used with these classical modules. These vintage electronic modules from the 1970s, sometimes called Silberlingen, made it possible to experiment with and to prototype all kinds of circuits and electronic principles. There were flip-flops, monoflops, a module with a signal amplifier for small sensor signals like this, and several different logic gates like the AND, NAND or the OR, NOR modules. This, by the way, is a DIY rebuild of such a module that can be switched between AND or OR functionality. Because these classic electronic modules were completely built out of discrete electronic components, the output signal could essentially only be used as a digital signal that can supply only a relatively small current. So, when eventually a motor or a lamp had to be controlled, a relay module with a built-in amplifier like this was often used in these days. But relays are still widely used today. This, for instance, is quite a modern card to be used for robotic projects with a Raspberry or Arduino microcontroller like these. An additional advantage of a relay is that the supply voltage of the motor or consumer is galvanically isolated from the rest of the circuit, and that with double changeover contacts, it's quite easy to set the direction of rotation of your motor. Most of the time, however, this is quite irrelevant and we just want to switch something on or off with our logic module or our microcontroller. Let's take this back to fischertechnik for a moment. For just regular switching, fischertechnik's next logical step in their so-called practicum kits was to move more towards a solid-state driver with a semiconductor. For instance, with the LST, the Leistungsstufe Baustein, from the electronic kit from 1981 that contained a module with two TIP 110 Darlington semiconductors. And even earlier, in 1977, in the experiments of the Elektronik Practicum, the principle of current amplifying was already explained with a regular BD135 NPN transistor. These experiments showed how lamps and motors could be supplied with sufficient current by amplifying with a transistor without the necessary use of a relay. The fun thing is that this basic method of switching is still very useful today. So for now, let's focus on switching things on or off with simple digital output signals. Sophisticated developments like stepper motor driver or H-bridges that enable you to control your motor's spinning direction are just not always necessary. For a lot of experiments, it will just suffice to switch on a lamp, electromagnet or engage, for instance, a pneumatic valve based on some digital logical level output. So just switch it on or off, and then a simple solution is probably best. So for now, let's take a closer look at how such a driver with an NPN transistor works. As you can see, I have some loads here, a resistor, a lamp and a motor. Let's switch on the motor. And the moment we provide more than 0.7 volts over the base to ground of this power switching transistor, the motor will go on, as you can see. just like that. And we can switch, for instance, also the lamp and the resistor in there, and things will continue to work. So as soon as the base of the transistor is high enough, in other words, as soon as we connect an active or high signal, the collector to emitter path of the transistor opens and the motor will spin, or the lamp will light, as we can show in this simulation. This is the most simple way of using a transistor for switching things on and off, and it's exactly the same as is used in fischertechnik's Leistings module. As long as it's open, no current flows, and if we close the input signal or we make it high, so to speak, there is around 10 milliamps going into the base of the switching transistor, which is fairly high. Perhaps we can improve on that. And this method of controlling actors and loads is still very useful today to control lamps, motors or pneumatic valves from the digital outputs of, for example, an Arduino. For instance, when you want to drive some pneumatic valves or a bell in your pinball machine model. For the Mr. Lemniscate model, I wanted to control 2 electromagnets from a flip-flop. So I've built my own flip-flop with driver outputs for this then, just because I didn't want to do the control with relays. It seemed quite unnecessary for me to add noise, delay and contact wear by using relays, which is in essence an electronic switch to drive other magnets. That's why I copied the original circuit diagram of the fischertechnik flip-flop and built it together with 2 IRF 520 MOSFETs in a fischertechnik cassette. This was of course quite a quick and dirty proof of concept, but the idea of simply having an output on all of these logic modules and electronic modules that could just supply a bit more driving current kept me busy. Because let's face it, how nice would it be to have this kind of power outputs on any flip-flop, mono-flop or, for instance, this DIY AND OR gate, just if you need it. Wouldn't it be possible, so to say, to design some kind of universal printed circuit board to easily provide any DIY logic module with driver outputs? Wouldn't it be wonderful to have a generic PCB that in my case can be placed at the bottom of these 3D printed Silberlingen casings? Such a bottom PCB could then accommodate the connectors necessary for connecting the looping through of the external 12-volt power supply, but it could drive and switch any motors or lamps, etc. However, while I was thinking about that, I could think of a few things that could make such a project even more useful. Firstly, I would like to equip such a driver module with a current limitation and, if possible, a short circuit protection. And fortunately, there turned out to be tried and tested methods for all of that. So let's investigate. But before we do that, let's enhance the basic circuit a little bit, because one of the disadvantages is that the power transistor needs a relatively large base current to be drawn from the controlling input. So let's add another transistor, like the one over here. The only task of this transistor is to provide the base current for the power switching transistor that we already had. And that's turning the motors and the lamps on and off. And as you can see, this extra transistor only requires 100 microamps on its base, so on the input. This makes the input less demanding and things can be switched with less current on the input. This is a great principle that makes it possible to switch simple loads on and off with just about any signal from, for instance, your Arduino or Raspberry microcontroller. However, this switched output is not yet current limited or short circuit proof. I came across quite an interesting article on Wikipedia about current limiting. I'll include a link to it on the project page of my website. Take a more in-depth look if you find this stuff interesting. It describes a fairly simple way to limit the current and dissipate the difference between the limited power and the actual drawn power in a transistor. Although the output transistor then might heat up, it has a much better chance of survival than if the current was not limited. Okay, so just take a look at this circuit. It's mainly the same as we have seen before. We've only included a resistors now here in series with the load. And as soon as the driver transistor opens and the lamp or the motor is switched on, a voltage will fall across it, depending on the current that is flowing, of course, here. The beauty of this is that this voltage will never ever be more than around 0.77 volts, because as soon as it reaches this voltage, this newly added transistor opens up, pulling the base of the power transistor low and cause it to close again, so throttling the current and causing the current to decrease. Okay, so there we have our current limiting. You could say that an equilibrium is established exactly when there is 0.77 volts across this shunt resistor. And because that has a fixed resistance value, we can calculate at what current it's limited now. Because the resistance is the voltage divided by the current. And the voltage, well, we use 0.778, which is a typical figure for that, and we divide it by our 260 milliamps being 0.26, and we get around 3 ohms for this shunt resistor. So if we want to limit the current to about 260 milliamps, this would mean that we have to include a resistor of around 3 ohms here. We can demonstrate the operation by switching on more and more consumers, and as you can see, the moment I'll switch on this 50 ohms resistor, it's already reached. The current is limited to around 260 amps. And when we add the short circuit switch over here, well, nothing more happens than the 260 milliamps that we already had. So the current is actively limited and we have a short circuit protection made over here. By the way, when inductive loads like magnets or motors are switched off, they tend to generate current themselves. So as you can see, I've also included a freewheeling or flyback diode here as a protection for the transistor to cancel out any generated current on these moments. Note, however, that the power transistor now is switched on and off at a very high frequency during this so-called current limiting, and as a result, heat may be developed. So take care that this situation will not last too long. And in practice, of course, this will never ever last too long. So you might say we have our current limiting and our short circuit protection in place. There is one thing we might change with this circuit. As you can see, the lamp and the motor and the loads are connected between the plus and the collector of the driver transistor. And wouldn't it even be more useful if the load could simply be connected between the output and the ground in so-called common mode, so sharing a common ground with the input? Because then the output could then also be used as a regular digital output and could also be used on digital inputs of other modules. Fortunately, this is quite simple by just flipping the whole circuit around by using PNP transistors instead of the NPN transistors we saw a moment ago. So now we have created the same schematics with the current limiting and the short circuit protection, but we can just connect our loads between the output and ground. And we could even use these outputs as digital outputs and connect them to other digital inputs. I took the time to develop a universal printed circuit board with which I could add 2 or, with all the components on, 4 of these driver outputs to my future electronic modules. Of course, your project might not have these limitations, but with only 4 by 7 centimeters, the available space in a Silberlingen casing is not very large at all. But in my case, 4 of these circuits could certainly fit. Well, enough theory for now. It's about time that we put this to the test in real life. This is my breadboard. Here I have the schematic of the simulation a moment ago, built with the BD132 and the current limiting transistor, a BC557 PNP transistor. Both are PNP transistors. As in the circuit diagram shown, this is the NPN transistor, that's a BC547, which provides the high impedance input of the circuit, so that's only used for switching. I will use my own power supply for the 12 volts, and I'll make the control signal for the input with my experiment board. That's just a 5-volt signal from one of these SR latches over here. By the way, you can find the DIY instructions for both of these modules on my website, fischertechnik.com, or check out the other videos here on YouTube that I made about these DIY electronic modules. If you find this fun or useful projects, don't forget to subscribe or leave a comment in the comment section of this video, and of course, I hope you give me thumbs up on this one as well. Okay, let's get back to our test bench. This is it's a 2.7 ohm resistor used as a shunt over here, so the current would theoretically be limited below 300 milliamps there. Probably somewhere between 260 and 290, just to be sure. I'll limit the 12 volts of my module to 300 milliamps in the module here. Let me program that. That will be our safety net then. If our short circuit protection will not be working, this will automatically fuse at 300 milliamps. So, okay, let's put things to the test. Okay, so things seems to be working. If we make this input high with the SR latch, the BD132 opens up and the motor is running. Very nice. So we can switch the motor on and off with just a low digital signal here. But now I'm very curious what happens if we short circuit the motor. So let's plug that straight into ground. Everybody ready? Here we go. The motor stops. We've got a max current below our safety net over here. So that's all within the set limit of 300 milliamps. Very nice, very nice. Let me feel what's going on here. Transistor is now switching on and off, so it might develop some heat. Yeah, ouch. Yeah, it does. Lots of power dissipation going on, certainly not that much as during a clear short circuit. Clearly a situation we should not allow to continue for too long, but the current limitation and the short circuit protection, well, have been demonstrated. And these are the finished PCBs. You might need only 2 drivers. For example, for a logic gate with only 1 output, you would like to switch both the normal and the inverted output signal off, or you might need all 4. In that case, just put all the components on your PCB to have 4 drivers available for your DIY electronic module in one go. I've made one that only has 2 drivers, for instance, to be used in a module that only has 1 logical output and its inverse logical signal. For instance, a 8-input NAND gate. One transistor will then provide a driver for the normal NAND output, and the other might facilitate the inverse NOT output signal, or this 4-transistor PCB that may be used to provide 2 output signals with their inverse signals. For instance, 2 4-input OR gates. An additional advantage of using the PCB for logic gates in this way is that only half of the transistors are active at any time. That would in any case limit any heat development. Although, of course, a heatsink can be placed like so. These are the connectors to which the 4 input signals come in. And the 4 switched signals with their power from the external adapter are returned to this connector. All we have to do now is to route these to the front of our own module in which we will use this board. You might have noticed that this output connector has 5 pins in its row. The middle one, that's the common mode ground for the outputs. The actual current is supplied by the externally connected power adapter. I devised my case with a little window on the back for 2 or 4 transistors with a TO126 package, and as we already saw, they can always be cooled with a small heatsink on the outside, if necessary. The power transistors are simply glued in place with a glue gun and later to be soldered to the printed circuit board when that's assembled at the bottom of the 3D printed case. So I have my driver PCBs in place for my future projects with logic gates and other electronic modules I might think up. I found it very instructive to find out how current limiting works and how I could implement it in a universally usable printed circuit board for any future DIY electronic project. I hope I inspired you to go that extra mile and make your own PCBs for this. Obviously, they are really more robust than the generic driver modules that you could order from the internet like these. So please let me know in the comments if this video was of any use to you and how you can use the principles for your own experiments with logic gates or the outputs of microcontrollers in general. For now, I hope you like this and I'm looking forward to seeing you with my next video. Until then, happy hacking!